All right, here we go, part 4. We want to calculate the mole fraction of each gas in the mixture we created in part E. I look at the mole fraction of hydrogen, that's the partial pressure of hydrogen divided by the total, or the number of moles of hydrogen divided by the total moles. 2.143 moles over 2.71 moles, I get 0.78 or 78%. This mixture is on a molar basis 78% hydrogen. I can do the same computation for methane on a molar basis and get 0.22. Now this should not surprise us. There are only two components in this mixture, hydrogen and methane. So once I've computed the mole fraction of one, then the mole fraction of the other is simply 1 minus the mole fraction of the first. Either way, I get 0.22 or 22%. All right, let's look at another problem. The mass of a butane lighter is recorded as 22.24 grams. It's used to collect butane gas in a tube by the method of water displacement. The temperature of the water bath is 22 degrees C. The barometric pressure in the lab was 755 millimeters of mercury. After the experiment, the butane mass is now only 22.03 grams. And once the experiment was complete, the height of the collection tube was adjusted so that the water levels inside and outside the tube were the same. Why did we do this? Well, the answer is in order to get the pressure of the bottle to be the same as the pressure of the atmosphere. It's easy to measure the atmospheric pressure. It's hard to measure the pressure inside the bottle. But if the water levels are the same, then the pressures must be the same. All right? Now, the next part is using Appendix B in the back of the book to determine the vapor pressure of water. This is a standard table. I'm not sure what page this is on in our book. In any event, you would be given a table of data from which you could discern this information, or they're flat out going to tell you what the vapor pressure of water is. At every temperature, water exerts a little bit more vapor pressure as the temperature goes up. So at our temperature of 22 degrees C, water has a vapor pressure of 19.83 torr. That's not very much compared to atmospheric pressure of 760. It's a very small amount. Now, when we get up to 100 degrees C, the vapor pressure would in fact be 760, but it's not. This is cold water. All right, so we want to use the equation on page 402. This is the right page number for our book, to calculate the partial pressure of the butane gas that was collected. That relationship says that the total pressure is equal to the gas pressure plus the vapor pressure of the water. I want to compute the gas pressure itself, so I need to rearrange this and get total pressure minus the pressure of the water. So 755 minus 19.83, I get 735.17. You would never in AP chemistry be doing anything with 5 significant digits for pressure, but there's a problem with the computation. Part J, the volume of the gas collected was 100 milliliters. Calculate the amount of butane gas in moles collected in this experiment, assuming that the temperature of the butane is the same as the water. Well, it's obvious we need to use PV equals nRT to compute the number of moles. So I take the pressure that I computed in part I times the volume of 0.1 liter divided by my gas constant for R and my temperature of 298, and I get 0.0040 moles. And I want to calculate the experimental value for the molar mass of butane. Well, 22.24 grams, which was the mass of the container before we vented the butane, minus 22.03, which is after, it gives me 0.21 grams of gas. I divide that by the number of moles I computed in the first part, and I get 53 grams per mole. We want to now calculate the percent error similar to the previous problem. I can go to my periodic table and determined the molar mass of butane is really 58.12. So my percent error is just the difference between those two masses divided by my accepted value, which is 58.12. And again, for this problem, like in the previous problem, we get about a 9% error. All right, let's go talk about the kinetic molecular theory of gases. There are 5 tenets to this theory, okay? Here are all 5 of them. So you're going to want to stop the video so you can write these down. You will need to know these. Number 1, gas particles are in continuous, rapid, random motion. 2, the volume of the particles themselves is negligible compared to the volume of the container. Part 3, there are no attractive or repulsive forces between these gas molecules. Consider them to be nothing more than billiard balls bouncing around a 3-dimensional pool table. Number 4, energy can be transferred during the collision, but as long as the temperature is constant, the average kinetic energy of the molecules is constant. And part 5, the average kinetic energy of the gas particles is proportional to the absolute temperature of the gas. All right. The diagram on the right can be found at the bottom of page 196. It shows the distribution of molecular speeds for nitrogen gas at 2 different temperatures, at 0 and 100 degrees. This is a very, very common picture. You can find this virtually anywhere on Google. So now we have true or false questions. Number 1, at a given temperature, each molecule in the gas sample is moving at the same speed. The answer to that question is false. We have a distribution of speeds inside a sample, even if it's the same. Even if the sample is pure nitrogen, we would expect to see a distribution of speeds. Not every molecule is going to have the same energy, therefore it won't be moving at the same speed. True or false? As the temperature of the gas is increased, the average speed of these gas molecules increases. Well, one look at the graphs and we can see that this is true. At 0 degrees, our average molecular speed is about 400 or so meters per second. And at the higher temperature of 100 degrees C, it's right about 500, maybe a little lower than 500 meters per second. The third one, true or false, the distribution curve tends to broaden as the temperature is increased, indicating the range of molecular speeds increases at a higher temperature. That also is true. We can see the higher the temperature, the broader, the wider the base of this curve is. All right, the average kinetic energy per molecule of a gas is 1/2 mv squared, where m is mass, v is velocity, and we can use this to compare the average speeds of different gases at a given temperature. So the question is, how do we arrange these gases in order of increasing average speed? I've got nitrogen, neon, and carbon dioxide. The heaviest gas moves the slowest. So we need to rank these gases in terms of their molar mass. In order of increasing speed, we need to put the heaviest gas first. So we get this order: carbon dioxide, nitrogen, neon. And then D. What does this diagram below tell us about the relationship between molecular speed and molar mass? Well, you can see that for gases, there's an inverse relationship between molar mass and molecular speed. Molecular speed tends to increase when molar mass is smaller. All right, we're going to talk about molecular effusion and diffusion. Although we probably will not see a quantitative calculation, in other words, a calculational problem involving Graham's law, it's a good idea for you to be able to use this equation. It's on page 197. All right, because you might need to talk about this equation. A certain gas has a rate of effusion, and effusion is the movement of a gas through a very small hole or a small orifice. This would be, for example, the rate of movement of a gas out of a bicycle tire stem valve, or perhaps the rate of effusion of uranium hexafluoride in a centrifuge. A certain gas has a rate of effusion that is twice as fast as that of methane, CH4. Calculate its molar mass. All right, we're going to call the unknown gas X. Now, what I have below that is called Graham's law. The effusion rate of gas 1 divided by the effusion rate of gas 2 is equal to the square root of the molar mass of 2 divided by the square root of molar mass of gas 1. So when I rewrite this, I see the rate of X divided by the rate of methane is equal to the square root of the molar mass of methane, which is 16, divided by the square root of the molar mass of X. I solve for X. I get X is 4 grams per mole. Likely, this is helium. All right. The last section is the deviation from ideal behavior. Gases tend to experience the largest deviations from ideal behavior under conditions of high pressure and low temperature. The particles of these ideal gases are assumed to occupy no space at all and not to have any attractive forces. However, the particles of a real gas have finite volumes and they do experience some attractive forces. So we want to explain why under conditions of high pressure, the volume of a gas tends to be greater than what we would predict. Well, you can see all this on page 201 in your book. The combined volume of the gas molecules themselves can be neglected when we're at low pressure. But when we get to high pressure, I can't really do that because now they take up an appreciable portion of the container volume, and that adds to the total volume predicted from the ideal gas law. All right, explain why under conditions of low temperature, the pressure of a gas tends to be smaller than what we predict. So at low temperature, attractive forces can no longer be ignored. And this is because at lower temperature, that means I've got lower kinetic energy, so molecules don't have the energy to overcome these intermolecular attractive forces, so they're more likely to stick together. And that reduces the number of collisions with the container wall, and that lowers the pressure. All right, part E. In general, gases tend to experience larger deviations from ideal behavior as the strength of their intermolecular attractive forces increases. For this reason, which of the following molecules is more likely to show a deviation from ideal gas? Hydrogen or water? And then we want to justify our answer, okay? So we need to consider which intermolecular force is the stronger force. In our case, we're only comparing hydrogen and water, and hydrogen only has a London dispersion forces, which we will learn about a little bit more in the next unit. But water has hydrogen bonding, which is a pretty strong intermolecular force, and therefore water would have the larger deviation from ideal gas behavior. All right, that concludes the note packet for our unit on gases. You should have completed this packet before our first day of class. When we get to class, we will be looking at quite a number of problems, both multiple choice and free response questions.